hydrogen energy system. So you can make hydrogen in various ways, but based on the solar energy, and then use it directly as a fuel or drive the fuel cell to drive your home appliance or automobiles. And then you produce the water as a single product, and then it could be recycled to make a hydrogen again. So you complete the environment ecologically very benign energy system. It is sometimes difficult to extrapolate the past to predict the future, but looking at the pattern of the energy usage for the last 300 years, the trend is very clear. From the fuel, we continuously replace the carbon with hydrogen coming from wood, coal, oil, and natural gas. And where we are headed for? Naturally, the pure hydrogen. And some estimates says that the solar hydrogen will cover 50% of energy market by the year 2100. So this is the revolution. So it will change everything, society, economy, and technology. And the photocatalysis will play I would say the major role in transforming this energy system. And as described by Professor Domen, you need some stringent condition to do this job. The band gap should be large enough. In addition to this requirement, you need some overpotential to take into account the inefficiency of the processes, and also its position should be located the more negative conduction band, more negative than hydrogen reduction potential, and the more positive than the water oxidation potential. And there are a number of the materials known for photocatalysis, but there are a number of problems for each material, which is also described by Professor Domen. And let me take over one of from his work. Okay, so this Domen's work, I think it is the great step of increasing the photoefficiency of water splitting reaction. There are many explanations, but one, I think the most important one is that you separate the reaction site, the hydrogen reduction site and oxidation site physically, so that you suppress the whole electron recombination, so that you increase the photo efficiency. So we started from here, and we also found that some class of layered perovskite are quite active for the complete water splitting under UV light, as high as the 23% of quantum efficiency. And under the same condition, the traditional Domen's material showed 5% under our reaction conditions. And of course, TiO shows very minimal or negligible water splitting activity. And all this catalyst material has the one nickel loading of the 1% and pre-treated according to the procedure suggested by Professor Domen. And this material is called the 100 layered perovskite because the direction of this interlayer is parallel to the 110 direction of the plane of the perovskite. And on the other hand, the Professor Domen's material is the 100 structure material, which is the interlayer plane is parallel with the 100 plane of perovskite. In addition to do that, there's a very important difference between two materials. First, Domen's material has the alkali metal or rock salt oxide in the interlayer space, and so that the water can penetrate and you can use the space as a vacuum site. But this material, there's no such an atom, external atom in interlayer space. You only have the full of oxygen, and water cannot penetrate into the space. Anyway, this material usually has the composition of the 227 material. And in this, the transmission electron microscope, you can see the layer structure clearly. It has interlayer space of about 3 angstrom. So we have thought about why this material is active, and here is only the conjecture. So don't ask too much about what the theory, but usual perovskite material has composition of AbO3. Usually A is the divalent the cation, and B is the tetravalent cation, making the stoichiometry of the AbO3. But our material is A is sometimes replaced by the trivalent material, or this B tetravalent material is replaced by the pentavalent material, making the total the cation valency plus 6. So the maintaining the same perovskite structure, this extra electron gives us the highly donor-doped n-type semiconductor. And what is the consequence of this the electron structure? And one very fortunate phenomenon for the photocatalysis in semiconductor science is that the formation of the band bending when semiconductor is immersed into solution, and so that you form this kind of the band bending, and the electron the follow this potential this way into the bulk of the solid semiconductor, and hole follow this way going to the surface and react with the solution, so that you can suppress the whole electron pairs by separating these two charges. And this thickness of this banding is called diffusion region, and it depends among other variables on the electron density. So if you have the highly donor-doped species, you decrease the thickness of this region, and then you increase the slope of this banding, then the charge separation may be much easier. And there could be other reasons, but this is the what we think the taking place at the moment. Now, in order to understand the material a little bit more, we try to determine the factors affecting the photocatalytic activity of our material. So we prepared a number of material, either the bulk type and layer structure, either having a cation valence of 6 or 7. This traditional perovskite material shows some activity, but it is quite little. And then, if you make a layer structure, the activity increase more than 30%. And then, if you replace this titanium with the pentavalent niobium or tantalate, or replace this strontium with the trivalent lanthanum, you have the 110 layer, the perovskite, all having the cation valence of +7. And this material showed the greatly improved photocatalytic activity. So it seems this special, particular electronic structure is the most important factor. When this material is heated at very high temperature to form this unstable phase, which has the bulk structure, photocatalytic activity reduced drastically. So it seems the most important factor is the electronic nature. The second one, the layer structure, is also very important for high activity. Now, because we found that the layer structure is also important, we investigate the effect of the slab thickness. So we vary the thickness of slab 1 layer and 3 layer, this 4 layer and infinite layer. This is bulk material. We didn't see much difference on the thickness effect, but all of them are much more active than bulk material. So the layer structure is important, but the number of layers is not that important. When you change the stoichiometry of the material just a little bit, say for example, the 5% increase or decrease of lanthanum affect the water splitting activity drastically. See, so it's very important to control the exact stoichiometry. And also the grinding method, whether you grind the precursors in dry state as a powder or grinding in ethanol solvent, we observed a big change in catalytic activity. The reason was if you grind the sample in ethanol, you form more uniform size and rounded the shape. It's not clear here, but in dry grinding, give the sample with a sharp edges and non-uniform particle distribution. And also, looking at the X-ray diffraction, you can see wet grinding gives the better crystallinity and also the higher phase purity. Here in dry grinding, you see the trace of the initial precursor oxide. So the preparation is a solid state reaction, which is very slow. So contact of the two precursor phase is very important to make the pure phase. In order to investigate the crystallinity and surface area effect, we sinter the catalyst at different temperatures. As you increase the sintering temperature, of course, relative crystallinity increases, which is defined by the ratio of the 210 X-ray diffraction P. And also, naturally, the BT area decreases continuously. The photocatalytic activity increases, show the maximum at 1273 K, and then decrease. So as you increase the relative crystallinity, activity increases, but then decrease because of the decrease in surface area. So what you want to have is the high crystallinity and high surface area, but it's very difficult because one variable changes these two factors in different ways. We try to optimize the nickel loading, which is used as core catalyst of our material. And we found that when we use the different perovskite, which was prepared at different temperatures, so it has different surface areas. And it has a very complicated pattern, but the optimum nickel content shows a very nice correlation with the surface area. So it seems that for fixed the perovskite surface, you need fixed amount of nickel in order to show the maximum water splitting activity. And why this thing happens again? Another conjecture. Okay, this is the model proposed by, I think, among others, the Domen a few years back on the role of the nickel oxide on this type of material. The one theory is that the nickel oxide is also the semiconductor, so it forms junction structure. So you have the N-type, the perovskite material, and P-type nickel oxide, and you have the nickel in between as an ohmic junction. And then, one electron generated on this perovskite and the hole generated on this nickel oxide collapses and disappears. But now you have the effective band gap of this much, so it gives the more driving force for the reaction. So if this is the true, you need a balance of this function and this function. That might be the source of the very nice correlation between the optimum nickel level and surface area. And another consequence of this structure is that the highest the quantum yield obtainable is just 50%, because you lose one electron and photons by this recombination process. So, of course, the chairman is standing up. This is the last slide. So, based on this type of experiment, we try to optimize our preparation. We optimized the grinding method, the temperature was optimized, the incubation method was optimized, and finally, we added the NaOH as a promoter. Then the quantum yield increased here steadily up to about 50%. So Professor Kudo also reported 50% of quantum yield, but we also observed the value close to the 50%. But this one might be close to the theoretical value. Thank you for your attention.